For the last few lectures, I have been talking about projective representations, or representations up to a phase. This is a situation which is relevant primarily for quantum mechanics, and here we have, corresponding to every symmetry group operation T, a corresponding unitary operator which acts on the Hilbert space, U of T, and these operators obey the rule U of T bar is either I phi T comma T bar, U of T T bar. We have also seen that such projective representations exist for all Lie groups. Even if you had a non-projective representation, one which obeyed U of T bar is U of T T bar, the standard kind of representation, you would always get a projective representation by just shifting the phases of the unitary operators involved. Such projective representations can of course be rendered non-projective by shifting the phases back, and these are considered to be effectively non-projective or trivial projective representations. You call a projective representation intrinsically projective if it is impossible to get rid of this phase phi of T comma T bar by redefining the phases of the individual unitary operators. And we had also spent quite some time in proving this key theorem that says that no representation of a given Lie group is intrinsically projective if the following conditions occur. The first condition is the generators of the corresponding Lie algebra can be redefined by shifting by a real number to eliminate all central charges. And the second condition is the parameter space of the group is simply connected. That is, all loops in the parameter space can be shrunk down to a point continuously. Our work so far has been perfectly general and is applicable to all Lie groups. What we are going to do next is apply these results specifically to the case of the Poincare group, which is of immense importance as far as relativistic quantum mechanics or later quantum field theory is concerned. We have seen in the first lecture of this section that a direct consequence of the extra phase factor into the I phi T comma T bar in the case of a Lie algebra representation is the additional term called a central charge. That is, whereas the commutation relations which the generators of a Lie algebra corresponding to a given Lie group obey is given for non-projective representations in the form TB, TC, the commutator is I times C A B C T A, sum over A of course, where C, A, B, C are the structure constants of the Lie algebra. In the presence of a projective phase, you get extra terms in the commutation relation, which has been highlighted in red here, is I times CBC times the identity. Here CBC are additional constants which of course obey CBC equals minus CCB. And in what follows, I am not going to write down the identity, it's always assumed to be present. It just simplifies the notation somewhat. Now this is the case for any general Lie group. We had already worked out earlier the commutation relations for the Poincare group. That is, a group for which the generators are generators of Lorentz transformation, J mu nu, and generators of space-time translations, P mu's. We had seen earlier that the commutation relations that will be obeyed in the case of non-projective representations is given by I times J mu nu comma J rho sigma is eta rho sigma J mu sigma plus eta mu sigma J nu rho minus eta mu rho J nu sigma minus eta nu sigma J mu rho. The part written in green on your screen right now. But if you're talking about projective representations, you will get an additional term, as I just explained, the central charge. And this central charge will of course depend on the indices mu nu and rho sigma. And we have written this term here as plus C rho sigma comma mu nu. Now the positioning of the indices here might come as a bit of a surprise. After all, the commutator of TB, TC had a central charge I times capital CBC. Here, at first sight, it looks like the two indices mu nu, which remember is one index, and rho sigma, this pair is another index, it looks like they have been reversed. That is, you get rho sigma comma mu nu rather than mu nu comma rho sigma, which you would have expected. But remember, in our standard Lie algebra commutation relations, this central charge term comes with an additional I in front. In the case of the Poincare generators, it's more convenient to write the commutator times an I, as we have done here. So that means that the central charge term will get an extra factor of I square, that is a minus 1. And because CCB is minus CBC, this extra minus sign is the same as flipping the order of the two indices. So you end up with C rho sigma comma mu nu. Proceeding along the same lines, we see that whereas for non-projective representations, I times the commutator of P mu with J rho sigma turns out to be eta mu rho P sigma minus eta mu sigma P rho. In the presence of projective phases, you will get an additional central charge term plus C rho sigma comma mu. Once again, the rho sigma and mu have been flipped to take care of the minus sign. And finally, we have the commutation relation between the translation generators. Since translations commute as group elements, the generators also commute as far as the Lie algebra is concerned. And for non-projective representations, we expect I, commutator of P mu comma P nu, to be 0. In the presence of projective phases, we might expect an additional central charge term, C nu comma mu. Of course, each of the central charge terms that you see on your screen right now, the ones written in red, are all multiplied by the identity. We are just omitting the identity for brevity of notation. Now, we will be using these commutation relations quite often in what follows. So it is perhaps a good time to pause a bit and take a look at the structure of the commutation relations here. This commutation relation, especially the one for the J's, looks pretty formidable and seems like it's something which is almost impossible to remember. However, you can actually get away without memorizing the whole thing and just remembering one very simple rule, and let me explain that to you. Let us first take a look at this term, which is I times the commutator of J mu nu with J rho sigma. On the right hand side, if you leave aside the central charge term, you have 4 terms which combine eta and j together. Let me warn you that eta is symmetric in its two indices, but j is antisymmetric. That is, eta mu nu is the same as eta nu mu, but j mu nu is actually minus j nu mu. So we have to be very careful about the order in which the indices occur, especially the ones on the j's, because changing them would introduce an extra minus sign. Now what we are going to do is figure out a way in which we can write down the first term on the right. And that's pretty easy. You just take the closest two indices on the two j's, that is nu and rho together, and put that pair on eta. The furthest indices mu and sigma, maintaining that order, goes on j. So that's how you get the first term. How do you arrive at the next few terms? Now for this, what I like to use are the basic symmetry properties of the commutator, which essentially follow from the fact that j's are antisymmetric. Note that if you interchange mu and nu, the j on the left is going to change sign, hence changing the sign of the commutator. The same goes for the case when you interchange rho and sigma. On the other hand, if you were to interchange both mu nu and rho sigma together, then you will expect an overall plus sign. Now that is all you really need to recover the other terms. Note that simultaneously interchanging both mu and nu and rho and sigma is effectively the same as taking the pair nu rho and swapping it with the pair mu sigma. And remember, this gives us a plus sign, And that is why the next term that we have written down has eta mu sigma and j nu rho. That is, the nu rho and mu sigma pairs have just gotten interchanged. To get the third term, all I have done is interchange the mu and nu indices at the expense of a minus sign. So instead of eta nu rho j mu sigma, you have minus eta mu rho j nu sigma. That is, the mu and nu of the first term has been interchanged to give you the third term. The fourth term, well, you can think of that as being obtained by interchanging rho and sigma in the first term at the expense of a minus sign. Or you could also say that all you have done is interchange the pair mu rho with the pair nu sigma in the third term. Of course, interchanging whole pairs of indices does not change signs. As a result, you still have a minus sign on the fourth term because the third term had a minus sign. So note that if you follow this basic mnemonic, it's pretty easy to remember exactly what the entire commutation relation is. So if you think of the indices on the j's as 1, 2, 3 and 4 in that order, that is mu, nu, rho and sigma, the pairing would essentially be 2 with 3 goes on eta, 1 with 4 goes on j, and the other terms on the right hand side can be figured out by simply using this swapping of the indices judiciously. Swap whole pairs with a plus sign, swap only one pair with a minus sign. Now coming to the next commutation relation, that is the one between p mu and j rho sigma, I times that of course. It's again very easy to remember. On the right hand side you have etas and p's, and the first term, the one with the positive sign, is simply obtained by taking the nearest indices on the p and the j. That is, mu is taken with rho, the two closest indices, and the other index, sigma, goes on the p. The other term is when you take mu and sigma, whereas the other index rho will now go to the p. But this is of course a term which you will get from the very first term that you have written down simply by interchanging rho and sigma. And because interchanging rho and sigma changes the sign of capital J on the left hand side, it is going to come with a minus sign. And finally, the commutator of p's is really rather trivial, so you don't really have to remember anything. At this point, let me issue a rather trivial warning for those small number of you who are following along these videos alongside looking at Weinberg's book. If you see Weinberg's book, he doesn't really write down the right hand side of this commutator in the same form. What he writes is the following: eta nu rho j mu sigma. The first term actually matches. The second term that he writes is eta mu rho j nu sigma, which is actually our third term here. That one matches. The next term that he writes is minus eta sigma mu j rho nu. And the last term that he writes is plus eta sigma nu j rho mu. Of course, in the presence of the projective phases, he also has this additional central charge term. Now, if you compare the two expressions that we have written down, this term, of course, is the same as this one. This, as we have already said, is the same as my third term. This one actually is the same as this term, except that here what Weinberg has done is that he has interchanged both mu and sigma. So he is writing sigma mu and rho and nu compared to this term that I have written down. Of course, the interchange of the sigma and mu does not change eta at all, but the interchange of rho and nu changes the sign of j. So that is why what was plus for me has landed up being minus for him. Very similarly, you can easily figure out that this term is exactly the same as this term. Of course, the expression I have is exactly the same as the expression that Weinberg has written down. It is just that I have found it very difficult to figure out the exact kind of process by which Weinberg would have written down the subsequent terms. I personally prefer the way I have written down these terms simply because it's easy for me to remember what goes where. You are of course free to use whichever version. I will use my version in the rest of this lecture. While on the topic of differences with Weinberg's text, I can also point out that Weinberg actually has one extra commutation relation here. The commutation relation of J with P, which he writes as eta mu rho P sigma minus eta mu sigma P rho plus an additional central charge term C rho comma mu nu. Of course, you can easily figure out this particular commutation relation from this one just by introducing a minus sign for the pj swap as well as rewriting the indices a bit, and it's easy to see that the two central charges that you have, C rho sigma comma mu in the upper one and C rho comma mu nu in the lower one, are simply related by a sign and of course reordering of the indices. I am not going to worry about this commutation relation at all in what follows, but that will actually introduce a small change in sign somewhere down the line, simply because Weinberg refers to C rho comma mu nu rather than C rho sigma comma mu. Coming back to more important things, the indices on the central charge, of course, has an antisymmetry. That is, if you interchange the two central charges, you are essentially talking about the commutator in the reverse order, so the central charge will change sign. And that is what you can see here. C rho sigma comma mu nu is minus C mu nu comma rho sigma. That follows from the fact that J mu nu comma J rho sigma changes sign if you were to swap the two J's. Similarly, you have C mu comma rho sigma being equal to negative of C rho sigma comma mu, which is the one which I just referred to, and the one which I will not really need to use much. And finally, you have C mu comma nu is minus C nu comma mu. Now, there are other antisymmetry conditions that you can easily think about. For example, if you took C rho sigma comma mu nu, this term here, and interchanged rho and sigma, so just wrote down C sigma rho comma mu nu, it's easy to see that the two are going to be related by a change of sign. That's simply because J rho sigma changes sign when you interchange rho and sigma. And you can think of similar negative signs that will occur whenever you are going to swap the indices in a given pair relevant for a J generator. Apart from this rather obvious set of conditions, the central charges do obey a series of more involved constraints, and these follow from the Jacobi identity. So, just to remind you, the Jacobi identity takes the following form. For any three operators A, B and C, the Jacobi identity essentially says that if you take this double commutator and then permute the three operators involved cyclically, the sum is going to be 0. In perhaps slightly more mathematical language, what we can say is that this is a reflection of the fact that the Lie bracket is not associative as a product, but obeys this more general associativity-like condition. Now, we have the four momentum operators here and the J mu nus, and depending on which ones of these we choose for our three operators in the Jacobi identity, we are going to get a series of different constraints. We can start with one in which all three operators involved are components of the momentum. Then we can have a Jacobi identity with two momenta components and one Lorentz generator. Then one momentum, two Lorentz generators. And then finally, all three operators could be Lorentz generators. So each of these could give us some constraints. The first case, where A, B and C are each some component of the 4 momentum or other, is seen to be trivially correct. Now, in the absence of central charges, this would be trivial because the commutators vanish anyway. So each of these double commutators are of course 0 and the sum is 0. Even in the presence of central charges, if you take 3 momentum components, 4 momentum components, then the inner commutator bracket would simply be a central charge, and that by definition commutes with everything else in the algebra. So the double commutator will definitely vanish for each of the 3 terms. So the sum is of course 0. So this particular constraint is trivially satisfied, and it does not give us any further condition on the central charges. Things will be different when we talk about the next level, which is 2 momentum components and 1 Lorentz generator. So this is our Jacobi identity when we take A to be J mu nu, B to be P rho, and C to be P sigma. What we will do is we will calculate each and every one of these double commutators separately and then add them together, specifically looking at the terms which contain the central charges. Please note that without the central charges, the Jacobi identity should already be satisfied, and that has to be ensured by the structure constants of the algebra. So we are not really going to pay too much attention to that part. We are going to look more seriously at the terms which involve the central charges. Let us now take a look at each of the 3 double commutators in succession. And because our original algebra was written with I times the commutator brackets, what I am going to do is supply an I square to each one of the 3 terms here. One I outside for the outer commutator bracket, another I for the inner bracket. This will make it easier for us to directly relate to the formulae that we have written down a while ago. Now note that I times the commutator bracket of P rho and P sigma is simply the central charge C sigma comma rho. So the next commutator bracket, of course, is going to vanish because the central charge, as we have kept said over and over again, commutes with everything. So the first term here simply vanishes. What about the second term with the extra I square factor? Now here, I will take the inner commutator first, and all we have to remember is that the commutator that we wrote down was essentially for P rho, of course I times that, and J mu nu, and that was eta rho mu, remember closer indices, P nu minus eta rho nu P mu plus the central charge term C mu nu comma rho. Here, the only thing that will happen is that we have to be careful about reversing the order of the commutator here. Remember, we have a P comma J commutator, whereas here we have a J comma P. That gives us a minus sign. So we just change the signs of these 2 terms. I get minus eta rho mu P nu plus eta rho nu P mu. You would have had an additional minus C rho comma mu nu here, but since that commutes with the P sigma, I could just as well drop it. So now you have to figure out what this particular commutator is. But that's straightforward. I times P sigma comma P nu is simply C nu comma sigma. So using the fact that etas are just numbers, that is components of etas are just numbers, I can pull them out of the commutator bracket and I get minus eta rho mu times C nu comma sigma from this commutator and plus eta rho nu C nu comma sigma from this commutator. Carrying out a very similar calculation for the third commutator bracket will simply give us this particular result. It's pretty straightforward. You should be able to work it out yourself with great ease. So now the sum total of all these three is 0, and therefore we get this particular relation. Minus eta rho mu c nu comma sigma plus eta rho nu c mu comma sigma plus eta sigma mu c nu comma rho minus eta sigma nu c mu comma rho equals 0. So the first of these two terms, of course, come from the second commutator bracket here, and the other two terms come from the third term out here. So this is the condition that our C's must obey. Now what we will do next is simplify this particular condition by a trick. What we are going to do is we are going to multiply both sides of this equation with eta nu rho and add up over the nu and rho indices, which are of course dummy indices now. In other words, we are going to contract both sides of this equation with eta nu rho. And what that is going to give me is pretty straightforward. If you multiply the eta rho mu by eta lower nu rho, remember this eta with upper indices is the inverse of this eta with lower indices, then the contraction over rho will immediately give you delta mu nu. So you get a minus delta mu nu here, c nu comma sigma of course. Eta rho nu, when you contract that with eta rho nu, basically you are multiplying a matrix by its inverse and then taking the trace of the resulting matrix, because you are also going to sum up over the other index. Now this, of course, gives us the trace of the identity matrix, the 4 by 4 identity matrix. So that just gives us the number 4. So this will give me 4 times c mu comma sigma. In the next term, of course, the etas have entirely different indices, sigma and mu, and the lower eta with lower indices have just rho, nu and rho. So there is no summation here, the summation is only here. But now, notice that eta nu rho is symmetric under the interchange of nu and rho, and c nu comma rho will change sign if we were to switch rho and nu. But that automatically means that this thing will change sign if we were to change the dummy indices into each other. And since interchanging the dummy indices cannot change a quantity, then this quantity must be the same as its negative, so it must be 0. Finally, the contraction of this term with eta nu rho, summation over nu, will actually give you delta sigma rho times c mu rho, of course. So the next step would be simply using the properties of the Kronecker delta to trivially sum this up. This sum is going to be minus c mu comma sigma, and this term is again going to be minus c mu comma sigma. So overall result on the left hand side is this is 0, and these three things add together to give you twice c mu comma sigma equals 0. So consistency with the Jacobi identity ensures that the central charge c mu comma sigma must vanish. So what we have obtained here is the following result. While it would be possible on the face of it that in the presence of projective phases the p commutation relation would acquire a central charge, consistency with the rest of the Poincare algebra, in particular consistency of the Jacobi identity of this kind, will insist that these central charges must vanish. You cannot have any central charge between p and p. We will now move up in the ladder of complexity and talk about the Jacobi identity, where two of the operators involved are Lorentz generators and one is a translation generator, that is a momentum component. Now this is what the Jacobi identity looks like in this case. The operator A is j lambda eta, B is j mu nu, and C is p rho. Of course, the double commutator here has to be added to its cyclic permutations in order to get 0. What we will do is we will take a look at each of these three terms 3 double commutators in succession. And perhaps I am being a bit more detailed than I need to be here. But after all, the devil is, as they say, in the details. So let's take a look at the first term here. After supplying the customary 2 factors of I so that we can relate to our standard results much more clearly. Well, the inner commutator I, j, mu, nu, p rho essentially is the standard one, again with a p and j switch. So what you have is minus eta rho mu p nu. That's the one which would have come out with a plus sign in the p rho j mu nu commutator, plus eta rho nu p mu. Of course, you would have to add a central charge term here, but I have not bothered to do that because in the next commutator with j lambda eta, the central charge term is going to simply vanish. We now have 2 commutators to calculate. Minus eta rho mu times the commutator of I times j lambda eta with p nu, and plus eta rho nu with a similar commutator again with j lambda eta and p mu. So if you directly calculate that using the standard rules, note all I have done here is I have taken the eta rho mu out, but the minus has become a plus because of the additional switch that we have to do between p and j to get to our standard form. And then what we get is eta nu lambda p eta. Remember, it's a commutator of p nu with j lambda eta. So that's what you're going to get here. Minus eta nu eta p lambda. I hope nobody is going to confuse the index eta here with the metric symbol eta. Sorry about the similar notation being used. In addition to that, you will have this plus c lambda eta comma nu, this particular central charge term. And you will get a similar expression from the other commutator, except for the fact that here eta rho nu will come out, and because you want to do a jp switch, it will come out with a minus sign. After that, we can collect the terms together. The p eta terms collected together gives you this. The p lambda terms collected together gives you this one. We are really not that interested in these terms. They may look more complicated, but ultimately we know that the Jacobi identity obeyed by the algebra without the central charges automatically ensures that terms of this kind, which would have been there even in the absence of central charges, must vanish. The presence of the central charge gives you these 2 new terms, eta rho mu c lambda eta comma nu minus eta rho nu c lambda eta comma mu. These are the terms that we have to pay more attention to. The next commutator, or rather double commutator that we need to consider, is this one. P rho is the outer operator, and then inside you have this commutator of j lambda eta with j mu nu. This of course is going to give a rather large expression on this side, but this is where our discussion on how to remember this commutation relation will be a fruit. And let me just see whether I can really write down all these terms without memorizing a lot. As we said, take the first index, the nearest 2 indices of the 2 j's, eta and mu, put them on the eta. And then take the outer 2 indices, lambda and nu, put them on the j. The next term, the one with the plus sign, is simply obtained by swapping these 2. So lambda nu comes here, eta mu goes there. The next term is one in which you have to interchange, say, mu and nu. So mu goes here, nu goes here, and of course you get a minus sign for that. The next term, I find it easiest to think of this as just taking this term and swapping the 2 pairs of indices, and this is what you're going to get. In addition to all this, of course, you will have the central charge term c mu nu comma lambda eta. Now, this term we have sort of been ignoring so far simply because on the next commutator, this is going to simply vanish. But now we have 4 pj commutation relations to evaluate. So we'll get 4 different terms. Each of them will come with its own central charge. So let's focus on the central charge part for the time being. P rho j lambda nu will give you a c lambda nu comma rho with of course eta eta mu outside. Then this one will give an eta lambda mu as an overall factor, but will give you a c eta mu comma rho. The next one will give you minus eta nu times this commutator. Once again, focusing only on the central charge piece, you get c lambda mu comma rho. And the final one will give you minus eta lambda mu times the central charge c eta nu comma rho. Now let's collect all the terms together, and I will not even bother to collect the terms involving the non-trivial generators here. As I have said before, the fact that Jacobi identity of course holds without the central charges ensures that these terms will cancel out. You can, of course, if you want, take a look at all these terms explicitly, but that's strictly speaking not very necessary. The new terms we have are obtained by collecting the central charge pieces from all of the four terms here. So this will give me four new terms involving central charges. Remember, we already have two from the first double commutator. The third double commutator is essentially very similar to the first one except for the positioning of the operators. And if you just carry out the same calculation, you will find that once again you will get terms involving the momentum operators, and in addition you will have two central charge terms. So in all you have 8 central charge terms which you can collect together and get to write this rather humongous looking expression. This is a condition which this kind of central charge, the ones with 2 Lorentz generator indices and 1 momentum index, 2, 1 kind of central charge, is going to obey. Now this looks pretty forbidding, of course, but we will see that if we carry out the same trick that the one that we did before, contracting with eta nu rho, we are going to get to a rather simple, or at least not so simple as the previous one, but a rather simple result nonetheless. So let's carry out the contractions. Contraction of this with eta nu rho is going to give me delta mu nu. This term will give me the 4, as was the case before. This term will give you delta lambda nu. This term will give you a delta eta nu. And then we will have 4 more terms. Of these 4 terms, this one again gives you a delta because one of the 2 indices with this eta lower and eta upper is common. So that's going to give you a contraction and gives you delta lambda rho here. This one will give you delta eta rho here. But for this term and this one, the indices on the upper eta or contravariant eta are completely different from the indices in the covariant eta here, and therefore no such contraction will take place between the etas. The contraction here will actually take place between the eta and the c. Same for this last term here. Now let's try to simplify this whole thing by using the delta symbols. So using the delta symbol, I can easily see that this term reduces to c lambda eta comma mu, which is of course the same as the one which we have here except with a factor of minus 4. This term on the other hand becomes a different index. The nu here on the c gets replaced by lambda, so you get c mu lambda comma eta. But the next term essentially gives you c mu eta comma lambda. So these are 3 separate different c's. Now what about these terms? Eta nu rho, c lambda nu comma rho. There is no antisymmetry argument here which will make this vanish, so this stays as it is. This one gives you c eta mu comma lambda, but note that these two both come with a plus sign, but c mu eta and c eta mu must be negatives of each other because they essentially come from j mu etas which change sign when you interchange the 2 indices. So this one and this one cancels. The next one here gives you another one which is going to cancel with this one. Again, the same sign, but mu lambda and lambda mu here means these two cancel each other out. The fourth term has to stay as it is. No further simplification really is possible. So what we get when you just take the 3c lambda eta comma mu to the other side is this expression. And that can be easily rewritten in this form. C lambda eta comma mu is basically going to be eta mu times this object into 1/3, of course. But this object is what you get when you contract the last two indices of the C with a lower index eta. And now the only free index left here is lambda. So we are going to call this C lambda. So C lambda by definition is 1/3 of eta nu rho C lambda nu comma rho. And you notice that a very similar thing happens in the next term. After you take the eta lambda mu out, you have a contraction of the last two indices on the C. And so this is going to be C eta. So this is the form in which I can write down C lambda eta comma mu. So notice that while each of the indices in lambda, C lambda eta comma mu could take 4 different values, which gives you 4 cube possibilities. Of course, antisymmetry would reduce the number substantially. But finally, what we see that each one of these can be written down in terms of the C lambdas, and there are only 4 such C lambdas. So ultimately, there are at the best only 4 independent C lambda eta comma mu's. Every such term can be written down in terms of C0, C1, C2, C3. Now, let's go back to our original condition which came from the Jacobi identity and try to check whether we can get any further condition on the C's. Now for this, what we need to do is start from the Jacobi identity inspired condition once again, this combination of the 8 C's which vanished, and in each one of them, for C lambda eta comma nu, place in an expression like this. Okay, the way in which you would really interpret this is, the first index goes to the back and sits on C. The other two indices, the closer two indices, go on the eta. That's with the plus sign. In the other sign, you just interchange the lambda and the eta to get a minus sign. So here, for example, the closer indices are eta and nu, and they are going to sit on top of the eta matrix, and then you have C lambda, and the minus sign will come in when you interchange eta and lambda between the two terms to get this one, and you can write down similar terms for all of them. Now, of course, you had 8 terms to begin with. Now each of these terms has been written down in terms of 2 such factors, so there are 16 factors to deal with, but let's just focus on one of them. Let's see what is a factor of C lambda overall. So C lambda is here. So I get eta rho mu eta nu, that's this term. Then you have a C lambda here, that's a minus eta rho nu eta mu. Then you have, okay, another C lambda here, that's a eta mu eta nu rho. And finally, you have another C lambda here, that's minus eta nu eta mu rho. Now let's take a look at what they become when you combine them. Eta rho mu, eta nu, and eta nu, eta mu rho are one and the same. Remember, eta is symmetric, so these two will cancel each other out. And similarly, this term and this term are exactly equal and they cancel each other out. So the coefficient of C lambda is 0, and it's pretty easy to figure out that that will happen for each of the C's here. And ultimately, what we have got above is not an equation which C's obey, but an identity. Both sides vanish identically. What that means is that the Jacobi identity does not give us any further conditions on the capital C's. So this is all you can really get out of the Jacobi identity, that the C lambda eta comma mu can be written down in terms of the eta components and a bunch of 4 numbers which we call C0, C1, C2, C3, which are defined, of course, this way. Now, let us go back to the original commutation relations where these occurred. We have these commutation relations between momentum and the Lorentz generators, P mu J rho sigma commutator, which had this additional C rho sigma comma mu term. In this, let's just put in the form that we have just written down. This thing is of the form eta sigma mu 0 minus the term which you get when you interchange rho and sigma. Notice that eta mu rho here is multiplied by p sigma in this term and minus c sigma in this term, so you can combine them together. Eta mu rho times p sigma minus c sigma minus eta mu sigma p rho minus c rho is this commutator. But now this commutator looks very much like the commutator we had without the central charges. All we have to do is define new operators p tilde mu to be just p mu minus these real numbers c mu. And if you do that, of course, that is not going to change the left hand side at all. P tilde mu j tilde rho sigma. We have not talked about j tilde yet, but if we shift j by a real number as well later on, we could talk of j tilde rho sigma. Here I've just talked about j rho sigma, but I could just as well imagine that later on we might want to shift the j's also, but by some real constants. That commutator is of course going to be the same as this commutator, and that is going to be eta mu rho p tilde sigma minus eta mu sigma p tilde rho. So what we have here is we have removed this central charge just by redefining my key operators. We have not redefined the j's as yet, but even if we did that, that's not going to make any change to this commutation relation. So at least the pj central charges can be shifted out or can be removed just by shifting the p's. What we are left with now is the most complicated of the double commutator terms, where each of the three operators involved are Lorentz generators. So just for the number of extra indices that this one has, sort of indicates that this is going to be more complicated. But let's go ahead anyway. After putting in the customary 2i factors, this j mu nu j rho sigma simply becomes, according to our prescription, eta nu rho j mu sigma plus eta mu sigma j nu rho minus eta nu sigma j mu rho minus eta mu rho j nu sigma, once again just flipping these pairs, plus the central charge c rho sigma comma mu nu, but that once again will not really survive till the next term. But now we have 4 commutators to calculate, and each one of the 4 is going to give you a central charge. Of course, it's also going to give you 4 extra terms involving j's from the jj standard commutator, but I'm not really even bothered about them. I've just indicated the first term here. In the other brackets, I have not even bothered to write down what they are, because once again, remember, the cancellation of those terms is guaranteed by the Jacobi identity, because we already know that without the central charge, what we have is a genuine, well-defined commutation relation. So, what this term is going to give is 4 terms involving central charges, which are extra. And from the symmetry of the situation, it's obvious that you are going to get 4 such terms from each one of the double commutators. I will not bother to work them all out. I'm just writing down this term, which is exactly what we have here, which came from the j lambda eta commutator with j mu nu commutator j rho sigma. Well, from the next cyclic permutation, of course with an extra I square, you are going to get this, which of course you can get from this simply by remembering that what you need to do is cyclically permute rho sigma, lambda eta and mu nu. And from the third cyclic permutation term, you are going to get this. So you will now have a 12-term condition on the double pair C's, that is C, mu sigma, lambda eta kind of thing. We will carry out the same check once again. We are going to contract with eta nu rho, and I'm simply going to write down the result here. You have seen enough details so far to be able to work this out. This one will give you a 4, that's this term. This one, eta nu rho, eta mu sigma, no contractions among etas. This is actually a contraction with the c's, but now notice that in the c's, if you interchange nu and rho, this will change sign, whereas this won't. And that immediately tells you that this term will vanish. Here, contraction with eta nu rho will give you a delta sigma rho, and that will mean that in the end you're going to change this rho into sigma. So you get C mu sigma lambda eta. You get another such term here again. So you get twice C mu sigma lambda eta from the first row. In the second row, you once again get an uncontracted term here. But now notice, here the nu and rho are from different pairs. Interchanging them does not necessarily change the sign. This one, you get a delta lambda rho, and that gives you this. Again, another delta eta rho, that will give you this. Once again, a term where there is no contraction between the etas, and a very similar looking term as this one, except that you have eta sigma. Here you have lambda and sigma uncontracted. Here you have eta and sigma uncontracted. Finally, from this term, one more similar looking term. But apparently the structure is different. Here the inner two indices are being contracted. Here the outer two are being contracted. But that's easily taken care of. All you have to do is switch this and this together. Remember, two switches, two minus signs gives you the same thing. So this is the same as C eta rho, comma, nu mu. Same structure once again. Two more terms which gives you deltas. One here, one this one, the other this one. This time the contraction is over rho to get the delta. And therefore the nu will be replaced by eta in the first term, and nu will be replaced by lambda in this term. So that's how you get this term and this one. And this once again is one in which the etas don't contract. The nu rho indices on eta contract with the outer indices on C. You can switch these two to get the same term. So now what you get after you move everything to one side, that is, you have twice C mu sigma comma lambda eta, which you can move to the other side and divide by the 2. And now what you get is the following. The first term simply becomes eta mu times half. The half of course comes from the 2 here. Eta nu rho, C lambda nu comma sigma rho. Then one more term which comes from this one. Okay, we have already changed the sign here. Notice by flipping this over, simply because you had plus 2 C mu sigma comma lambda eta. Going on the other side, give you minus 2. So we had to change the sign here. We did the same with this, just change the minus to plus. We got ended up with this term. And we got 2 more of these terms. But then it's easy to see that these 4 terms, each of them have the same structure. Note, nu rho is contracted here with nu and rho, the second and fourth. Let's stick to that. And then here nu rho is contracted with rho and nu. Well, doesn't matter, because you can just as well use the fact that this is rho nu, because after all eta is symmetric, and then if you want you can relabel the rho and the nu to get back to the same form. Once again, the second and the fourth indices contracted. Here also nu rho, rho nu, second and fourth indices contracted. Nu rho, second and fourth indices contracted. So each of these terms have exactly the same structure, and so we end up with eta mu times the free indices left here are lambda and sigma. So this is called C lambda sigma. This one will have free indices eta and mu, called C eta mu. This one C lambda mu, and this one C eta sigma. So we have these 4 terms where any one of these essentially is defined by this contraction, eta nu rho, and the contraction is between the second and the fourth. Here, whether you have nu rho or rho nu doesn't really matter because eta anyway is symmetric. Now, one lengthy calculation that we can do after this is start with this 12-term condition that we get from the Jacobi identity, put in this particular form that we have derived, this 4-term particular form that we have derived for the C mu sigma lambda eta. So, these 4 to the 4, 64 C's have now been expressed in terms of 16 C lambda sigmas. And we can push this all in and then try to see whether you get any further conditions on the C lambda sigmas from this. And, well, there's no surprise really. You don't really get any further conditions if you just club everything together. That's of course a long calculation because you have 12 terms originally. Each one of them has this 4-piece replacement. So you get 48 total terms. But if you just look at the coefficient of one term, say C lambda sigma, and do it carefully, you will find that that vanishes. And this happens for each one of the C lambda sigmas. So there are no further conditions involved. This one is the only condition, that the C mu nu lambda sigmas can always be written down in terms of C lambda sigmas in this particular manner. Now this particular expression might actually look rather familiar. This essentially looks almost the same as the JJ commutation relation that we had without central charges. And that actually is going to come in very handy for us. Remember, C mu sigma comma lambda eta is a central charge which appeared in the commutation relation between J lambda eta and J mu sigma. And this was the commutation relation. Now, if you take this C mu sigma comma lambda eta and replace it by the constraint that we have just found out, in terms of this double index C's, you are going to get this. And note that now each one of the terms in the upper row has a corresponding term with the same sign, same coefficient eta in the lower row. And that means you can just club them together. And if you were to now define G lambda sigma plus C lambda sigma as J tilde lambda sigma, then this two together will give you J tilde eta mu, these two together will give you J tilde lambda mu, and these two together will give you J tilde eta sigma. And of course, the commutator between J tilde lambda eta and J tilde mu sigma is going to be the same as the commutator between J lambda eta and J mu sigma. After all, the C's don't give you any additional terms in the commutation. And by doing that, we will now get a new commutation relation which does not have the central charges at all. So by redefining the J's in this way, by shifting the J's, we have been able to get rid of the central charges completely. So the upshot of all this is, while we could actually have projective representations for the Poincare algebra, we see that at least this does not leave us any trace in terms of non-trivial central charges. We can have central charges, but you can always get rid of the central charges just by shifting the definition of the operators involved. Now, this last calculation that we did a while ago, the one involving 3 J's and their Jacobi identity, the most complicated one that we have carried out, is one which we did not really have to carry out. This is because the J's are generators of the Lorentz algebra, and we know technically that a Lorentz algebra is something called a semi-simple Lie algebra. It has only one abelian invariant subalgebra, and that is a trivial one. Now, if you don't know enough Lie algebra theory to understand what this means, don't bother because we have already worked out everything explicitly so far. All I'm saying is that there is a standard result in Lie algebra theory which says that if you have a semi-simple algebra, I've written groups here but I really meant algebra, any central charges that you can add are always removable. You can just redefine the generators and get rid of them. This is a result from Lie algebra theory. So if the Lorentz algebra had been all that we had been worried about, and that's what we actually showed in our last calculation, I could have, even without any calculation, just from this theorem, have said that the central charges can be removed. However, the Poincare group and its corresponding algebra is not semi-simple. It does have an abelian invariant subalgebra. Once again, what I've written here is wrong. It should be the Poincare algebra is not semi-simple. It's true that the corresponding group is also not semi-simple, but that's not relevant here. The p-mu's, they form an abelian invariant subalgebra. Abelian just means the p's commute among themselves, and invariant simply means that if you take the commutators of p's with every one of the generators of the system, here of course that can only mean p's and j's, you're only going to get a combination of p's, which we have already seen to be true. So Poincare group does have a non-trivial abelian invariant subalgebra. So at least for the full Poincare algebra, this proof is actually necessary. The theorem that we quoted a while ago will not guarantee the vanishing of the central charges. It of course does not tell you that the central charges cannot be made to vanish. It just doesn't give you this easy route of just invoking a theorem from the algebra to say the central charges must vanish. What we have done, of course, is calculate explicitly and shown that these central charges must vanish. Let me remind you once again about our key theorem. We say that in order that a Lie group does not have any intrinsically projective representation, two conditions must be obeyed. Any central charges of the algebra should be removable. We have already proven today that that's true. The other question would be about whether the parameter space is simply connected or not. We are going to address that question in the next lecture, and there is going to be a surprise there for you. Or maybe, if you have already done advanced quantum mechanics, that may not come as a surprise really, but it may come as a result that you already know, but you will now understand why that result works the way it does. But that's for the next lecture.